situation encountered involved a Siemens panel seemingly intended for high Lake Delta service, yet the available breaker slots were designed for 120/240 volts/rated breakers. Compounding the issue, the panel's nameplate indicated a 120/208Y not Delta service. The implemented solution involved utilizing two-pole breakers rated at 240 volts for the new circuits. However, this approach presents several potential problems. Firstly, voltage imbalance. Using two-pole breakers on a 120/208Y service can lead to voltage imbalance, particularly if the new circuits carry substantial loads. This imbalance can negatively impact the lifespan of motors and other equipment sensitive to voltage fluctuations. Secondly, mislabeling. The panel's labeling might not accurately reflect the actual 120/208Y service configuration. This discrepancy could cause confusion and pose safety hazards for electricians working on the system in the future. Thirdly, violation of code. Employing breakers rated for a higher voltage than the service voltage constitutes a violation of the National Electrical Code (NEC). The NEC establishes safety standards for electrical installations, and using inappropriately rated components can compromise the system's safety and compliance. I recommended an ideal solution would be to upgrade the panel to one specifically designed for a high leg delta configuration, equipped with breakers rated for 208 volts. This upgrade would ensure proper voltage balancing across the circuits, mitigating the risk of equipment damage due to imbalance. It would also eliminate the code violation associated with using overrated breakers. To elaborate further on the high leg delta configuration, it's essential to understand its characteristics and potential challenges. A high leg delta system is a three-phase electrical service where one phase, often referred to as the high leg or wild leg, has a higher voltage to neutral than the other two phases. In a 240 volts high leg delta system, the voltage from two of the phases to neutral is 120 volts, while the voltage from the high leg to neutral is approximately 208 volts. This configuration is commonly used in older industrial and commercial buildings to provide both single-phase and three-phase power. The challenge with a high leg delta system arises when trying to balance the load across the three phases. Single-phase load should be distributed as evenly as possible to prevent voltage imbalances. The high leg should only be used for three-phase loads or loads specifically designed to handle the 208 volts to neutral voltage. Using standard 120 volts equipment on the high leg will result in damage or failure. In the described scenario, the mismatch between the panel's intended configuration high leg delta and its actual configuration 120/208Y creates confusion and potential hazards. A 120/208Y system is a three-phase, four-wire system where the voltage between any two phases is 208 volts, and the voltage from any phase to neutral is 120 volts. This system is commonly used in commercial buildings for general power distribution. Using two-pole breakers rated for 240 volts on a 120/208Y system might seem like a workaround, but it can lead to several problems. Firstly, the breakers might not be properly calibrated for the low voltage, which could affect their tripping characteristics. Secondly, the voltage imbalance caused by unevenly distributed loads can overload one or more of the phases, leading to overheating and potential equipment failure. To address the voltage imbalance issue, it's crucial to measure the voltage on each phase and ensure that the loads are evenly distributed. If the voltage imbalance exceeds a certain threshold, typically 3%, corrective measures should be taken. These measures might include redistributing the loads, using voltage regulators, or upgrading the service to a more balanced configuration. Another important consideration is the panel's labeling. The panel should be clearly labeled to indicate the actual service configuration, whether it's high leg delta or 120/208Y. This labeling should include the voltage between phases, the voltage from each phase to neutral, and any specific instructions or warnings related to the high leg. Proper labeling is essential for preventing confusion and ensuring the safety of electricians and other personnel working on the system. The NEC provides specific guidelines for electrical installations, including the selection and application of breakers. Section 240. 85 of the NEC addresses the use of slash-rated breakers, which are breakers with two voltage ratings separated by a slash, such as 120/240 volts. The NEC permits the use of slash-rated breakers in systems where the nominal voltage between any two conductors does not exceed the lower of the two voltage ratings. In the described scenario, using 120/240 volt slash-rated breakers on a 208 volt system would violate this rule. The NEC also requires that breakers be suitable for the specific application and voltage. Using breakers that are not properly rated for the system voltage can compromise their ability to protect the circuit from overloads and short circuits. In addition to upgrading the panel, another potential solution would be to install a separate transformer to provide the required 208 volts for the new 8-track equipment. A transformer can step down the voltage from the existing 120/208Y system to 208 volts, providing a dedicated power source for the equipment. This approach would eliminate the need to use the high leg of a high leg delta system and ensure proper voltage balancing. When selecting a transformer, it's important to consider the kVA rating of the transformer, which should be sufficient to handle the load of the 8-track equipment. The transformer should also be properly grounded and protected from overcurrents. In summary, the described situation highlights the importance of understanding the different types of electrical services and the potential problems that can arise from using mismatched components. The ideal solution would be to upgrade the panel to one specifically designed for the actual service configuration and equipped with properly rated breakers. Alternatively, a separate transformer can be used to provide the required voltage for the new equipment. Proper labeling and adherence to the NEC guidelines are essential for ensuring the safety and reliability of the electrical system. Furthermore, it's crucial to consider the long-term implications of any electrical modifications. Using improper components or configurations can lead to premature equipment failure, increased energy consumption, and potential safety hazards. Investing in a properly designed and installed electrical system can save money and improve safety in the long run. The NEC also addresses the issue of voltage drop, which is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or fail prematurely. Section 210.19 of the NEC provides guidelines for minimizing voltage drop in branch circuits. To minimize voltage drop, it's important to use conductors of adequate size and minimize the length of the circuit. The NEC provides tables that specify the minimum conductor size for different ampacities and voltage drops. In addition to conductor size, the type of conductor can also affect voltage drop. Copper conductors have lower resistance than aluminum conductors, so they are generally preferred for long circuits or circuits with high ampacities. Another important aspect of electrical safety is grounding. Grounding provides a path for fault current to flow back to the source, tripping the breaker and preventing electrical shock. The NEC provides detailed requirements for grounding electrical systems. Section 250. 24 of the NEC requires that all electrical services be grounded. The grounding electrode system should consist of a grounding electrode conductor connected to a grounding electrode, such as a ground rod, metal water pipe, or concrete encased electrode. The grounding electrode conductor should be sized according to the NEC tables. In addition to grounding, bonding is also important for electrical safety. Bonding connects all metal parts of the electrical system together, creating a low impedance path for fault current. The NEC requires that all metal enclosures, raceways, and equipment be bonded together. Bonding conductors should be sized according to the NEC tables. Proper grounding and bonding are essential for preventing electrical shock and ensuring the safety of personnel working on the electrical system. It is also worth noting that older electrical systems may not meet current code requirements. Over time, the electrical codes are updated to reflect new technologies and safety concerns. When working on older electrical systems, it's important to identify any code violations and bring the system up to current standards. This may involve replacing outdated wiring, installing new breakers, or upgrading the grounding system. In addition to code compliance, it's also important to consider the overall condition of the electrical system. Older electrical systems may have deteriorated wiring, corroded connections, and other problems that can compromise their safety and reliability. A thorough inspection of the electrical system can identify any potential problems and allow for timely repairs. Regular maintenance is also essential for keeping the electrical system in good working order. This includes inspecting breakers, tightening connections, and testing ground fault circuit interrupters, GFCIs. GFCIs are designed to protect people from electrical shock by detecting ground faults and quickly interrupting the circuit. They are required in certain locations such as bathrooms, kitchens, and outdoor areas. In addition to GFCIs, arc fault circuit interrupters of SIs are also becoming more common. SIs are designed to protect against electrical fires by detecting arc faults, which are dangerous electrical discharges that can ignite flammable materials. They are required in certain locations, such as bedrooms and living rooms. When working on electrical systems, it's important to use proper safety equipment and follow safe work practices. This includes wearing appropriate personal protective equipment, PPE, such as gloves, safety glasses, and insulated tools. It's also important to de-energize the circuit before working on it and to verify that the circuit is de-energized using a voltage tester. Working on energized circuits can be extremely dangerous and should only be done by qualified professionals. In conclusion, electrical work requires a thorough understanding of electrical principles, codes, and safety practices. It's important to consult with qualified professionals and to follow all applicable codes and regulations when working on electrical systems. By taking the necessary precautions, you can ensure the safety and reliability of the electrical system and prevent accidents. When dealing with existing electrical systems, especially in older buildings like the funeral home mentioned, it is vital to thoroughly document the existing conditions before undertaking any modifications. This documentation should include detailed photographs, voltage and current measurements at various points in the system, and a complete inventory of all electrical components, including breakers, wiring, and grounding systems. This information will serve as a baseline for future work and can help identify any existing problems or potential hazards. Furthermore, it is recommended to consult with a qualified electrical engineer or a master electrician with experience in working with older electrical systems. These professionals can provide valuable insights and guidance on the best approach to take, ensuring that the modifications are safe, code compliant, and compatible with the existing system. They can also help identify any potential issues that might not be immediately apparent, such as hidden wiring or outdated components. In addition to the technical aspects, it is also important to consider the aesthetic impact of the electrical modifications, particularly in a building with historical significance like a funeral home. The goal should be to minimize the visual intrusion of new electrical components while still meeting the functional requirements. This might involve using concealed wiring, selecting aesthetically pleasing fixtures, and carefully coordinating the placement of electrical outlets and switches. It is also important to communicate effectively with the building owner or manager throughout the process. They should be informed of the scope of work, the potential impact on the building, and any potential disruptions to their operations. Their input should be considered when making decisions about the electrical modifications. Finally, it is crucial to maintain accurate records of all electrical work performed. This should include detailed drawings, specifications, and test results. These records will be valuable for future maintenance and troubleshooting and can also be helpful in demonstrating compliance with electrical codes and regulations. In summary, electrical modifications in older buildings require a careful and methodical approach. Thorough documentation, expert consultation, attention to aesthetics, effective communication, and accurate record keeping are all essential for ensuring a successful and safe outcome. Let's also consider the specific implications of adding new HVAC equipment to an existing electrical system. HVAC equipment, especially air conditioners and heat pumps, can draw significant amounts of power, particularly during startup. This can put a strain on the electrical system and potentially overload circuits if the system is not properly sized. Therefore, it is crucial to perform a load calculation to determine the total electrical load of the new HVAC equipment and to ensure that the existing electrical system has sufficient capacity to handle the additional load. The load calculation should take into account the size of the HVAC equipment, its energy efficiency rating, and the operating conditions. The load calculation should also consider any other electrical loads that might be operating on the same circuits, such as lighting, appliances, and other equipment. If the load calculation indicates that the existing electrical system is not sufficient to handle the additional load, it might be necessary to upgrade the service entrance, the panel board, or the wiring. Upgrading the service entrance involves increasing the size of the conductors that bring power into the building from the utility company. This can be a significant undertaking and might require coordination with the utility company. Upgrading the panel board involves replacing the existing panel board with a larger one that has more breaker slots and a higher ampacity rating. This can provide additional capacity for the new HVAC equipment and any other future electrical loads. Upgrading the wiring involves replacing the existing wiring with larger conductors that can handle the increased current. This can be a time-consuming and costly process, but it is essential for ensuring the safety and reliability of the electrical system. In addition to upgrading the electrical system, it is also important to ensure that the new HVAC equipment is properly grounded. Grounding provides a path for fault current to flow back to the source, tripping the breaker and preventing electrical shock. The HVAC equipment should be grounded according to the manufacturer's instructions and all applicable electrical codes. It is also important to ensure that the HVAC equipment is properly protected from overcurrents. Overcurrent protection devices, such as breakers and fuses, are designed to interrupt the circuit in the event of an overload or short circuit. The overcurrent protection devices should be sized according to the ampacity of the HVAC equipment and the wiring. Finally, it is important to test the electrical system after the HVAC equipment has been installed to ensure that it is functioning properly. This should include testing the voltage, current, and grounding system. Any problems should be corrected before the HVAC equipment is put into service. In summary, adding new HVAC equipment to an existing electrical system requires careful planning and execution. A load calculation should be performed to determine the total electrical load of the new equipment, and the electrical system should be upgraded if necessary. The HVAC equipment should be properly grounded and protected from overcurrents, and the electrical system should be tested after installation. By taking these precautions, you can ensure that the new HVAC equipment operates safely and reliably. Furthermore, when dealing with 208-volt circuits, it's important to use equipment that is specifically rated for that voltage. Using 240-volt equipment on a 208-volt circuit can result in reduced performance and premature equipment failure. 208 volts is a common voltage in commercial and industrial buildings, and it is often used for powering HVAC equipment, lighting, and other appliances. 208 volts is derived from a three-phase electrical system, and it is the voltage between any two phases. When selecting equipment for a 208-volt circuit, it is important to check the voltage rating on the equipment to ensure that it is compatible. The voltage rating is typically indicated on a nameplate or label on the equipment. If the equipment is not rated for 208 volts, it should not be used on that circuit. Using equipment that is not properly rated for the voltage can be dangerous and can result in electrical shock, fire, or equipment damage. In addition to the voltage rating, it is also important to consider the current rating of the equipment. The current rating is the maximum amount of current that the equipment can safely draw. The current rating should be equal to or greater than the current that the circuit is designed to carry. If the equipment draws more current than the circuit is designed to carry, the breaker can trip or the wiring can overheat. When selecting wiring for a 208-volt circuit, it is important to use conductors that are sized appropriately for the current. The NEC provides tables that specify the minimum conductor size for different ampacities. It is also important to use conductors that are rated for the voltage of the circuit. In addition to the wiring, it is also important to use properly rated breakers for the circuit. The breakers should be sized according to the ampacity of the circuit and the equipment that is connected to the circuit. The breakers should also be rated for the voltage of the circuit. Finally, it is important to test the 208-volt circuit after it has been installed to ensure that it is functioning properly. This should include testing the voltage, current, and grounding system. Any problems should be corrected before the equipment is put into service. In summary, working with 208-volt circuits requires careful attention to detail. It is important to use equipment that is properly rated for the voltage and current of the circuit, and to use wiring and breakers that are sized appropriately. The circuit should be tested after installation to ensure that it is functioning properly. By following these precautions, you can ensure that the 208-volt circuit operates safely and reliably. Let us further consider the ramifications of using mismatched breakers. Breakers are designed to protect electrical circuits from overloads and short circuits. They do this by interrupting the flow of current when it exceeds a certain level. Breakers are rated in amps, which indicates the amount of current that they can safely carry. They are also rated in volts, which indicates the maximum voltage that they can safely interrupt. When selecting breakers for an electrical circuit, it is important to use breakers that are properly rated for the circuit. Using breakers that are too small can result in nuisance tripping, which is when the breaker trips unnecessarily. Using breakers that are too large can result in damage to the wiring or equipment. The NEC provides guidelines for selecting breakers for different types of circuits. The guidelines take into account the ampacity of the circuit, the type of equipment that is connected to the circuit, and the ambient temperature. It is important to follow these guidelines when selecting breakers. In addition to the amp rating, it is also important to consider the voltage rating of the breakers. The breakers should be rated for the voltage of the circuit. Using breakers that are not properly rated for the voltage can be dangerous and can result in electrical shock, fire, or equipment damage. When installing breakers, it is important to follow the manufacturer's instructions. The breakers should be properly seated in the panel board and should be securely connected to the wiring. It is also important to test the breakers after they have been installed to ensure that they are functioning properly. This can be done by using a breaker tester. If a breaker fails to trip when it should be replaced immediately. Breakers are an essential safety device in electrical circuits. They protect against overloads and short circuits, which can cause fires and electrical shock. It is important to select and install breakers properly and to test them regularly to ensure that they are functioning properly. Improperly rated breakers can lead to hazardous situations. For example, if a breaker is rated for a higher current than the wiring can handle, the wiring can overheat and cause a fire before the breaker trips. Similarly, if a breaker is rated for a low voltage than the circuit, it might not be able to interrupt the current in the event of a fault. This can also lead to a fire or electrical shock. In addition to the amp and voltage ratings, it is also important to consider the interrupting capacity of the breakers. The interrupting capacity is the maximum amount of current that the breaker can safely interrupt. The interrupting capacity should be greater than the available fault current at the point where the breaker is installed. The available fault current is the amount of current that would flow in the event of a short circuit. The available fault current can be calculated using a fault current calculator. If the interrupting capacity of the breaker is less than the available fault current, the breaker can fail to interrupt the current in the event of a short circuit. This can lead to a fire or electrical shock. When selecting breakers, it is important to consult with a qualified electrician to ensure that the breakers are properly rated for the circuit and that the interrupting capacity is sufficient. It is also important to test the breakers regularly to ensure that they are functioning properly. By following these precautions, you can ensure that the electrical system is safe and reliable. As a final point, consider the importance of regular electrical inspections. Regular electrical inspections are essential for maintaining the safety and reliability of an electrical system. Electrical systems can deteriorate over time due to wear and tear, corrosion, and other factors. Regular inspections can identify potential problems before they become serious hazards. Electrical inspections should be performed by qualified electricians. The electrician should be trained to identify potential problems and to make recommendations for repairs or upgrades. The frequency of electrical inspections depends on the type of electrical system and the environment in which it is located. For example, electrical systems in industrial buildings should be inspected more frequently than electrical systems in residential buildings. Electrical inspection should include a visual inspection of all electrical components, including wiring, breakers, outlets, and switches. The electrician should also test the operation of the breakers and ground fault circuit interrupters, GFCIs. The electrician should also check the grounding system to ensure that it is functioning properly. After the inspection, the electrician should provide a written report that summarizes their findings and makes recommendations for repairs or upgrades. The report should also include a list of any code violations that were identified. It is important to address any code violations promptly. Code violations can create safety hazards and can also result in fines. Regular electrical inspections are a cost-effective way to maintain the safety and reliability of an electrical system. By identifying potential problems early, you can prevent costly repairs and avoid accidents.